Well, good evening, and sorry this stream is a little bit late. Family things, they always seem to get in the way of real life. Anyway, welcome to my little stream this evening. Yes, I've got a fun one this evening. This is an idea that I've had buzzing around in my head for a while. Is how can I do good VGA capturing of old computers? I do have HDMI capturing, which works pretty well. I also have little anything to HDMI adapters. I've got a composite to HDMI and a VGA to HDMI adapter, which the composite one works beautifully. Got no complaints at all about that. The VGA one, though, only seems to work for specific resolutions. And the most annoying thing is those specific resolutions don't include DOS resolutions. Only things like 640 by 480, 800 by 600, that sort of thing. The higher resolutions. When you get down to things like 320 by 200 or even just 80 column text on a PC, it just can't handle it. So I need some better way of doing VGA capturing. And a thought crossed my mind last night. How about, it won't be perfect, but how about if I intercept the digital data before it gets to the DAC of the video card and capture that with something like a Raspberry Pi or something along those lines? The problem with that is most video cards, the DAC is integrated into the actual main chip. If I take this Voodoo 3000 for example, you've got basically the main chip, which is hidden under here at the moment, RAM chips, BIOS, and that's it. On older like CGA cards, MCA cards, whatever, the DAC, or RAM DAC as it's known as, is external to the main chip. So I could, using one of those, I could actually intercept the data quite happily. On things like the Amiga, the output of Denise is parallel digital data, which then gets converted externally using what's called the hybrid in this case, which is just a little circuit board with a DAC on it. So you can intercept the video before it gets to that and get good quality out of it. But with these modern cards, here's another example, the Matrox G450. Again, it's one chip, the memory, and is that not quite sure what the other chip on here is, but it's basically the interface controller, I think, that goes between PCI and the main chip. But again, there is no DAC because the DAC is integrated into the main chip, so you can't get at that data. Except you can, possibly, sometimes. All these graphics cards, these older graphics cards, all have an extra 26 pin connector on them. That's called the VESA feature connector, and it's designed for connecting video decoders and video encoders, even, or all sorts of things like that, onto the graphics card. It's sort of the forerunner to modern SLI, where you can chain multiple graphics cards together. And what this does is this hooks in between the graphics processor and the RAM DAC inside the chip. So, result, you might think. That's exactly what we want, but there is a catch. This connector only has 26 pins. A full VGA signal would have at least 24 graphics bits to it, 8 red, 8 green and 8 blue, plus all the sync signals, plus ground. There's no way you can fit all that into that one connector. So they don't. That only has 8 bits of data on it. It only really has any use for VGA palette-based resolutions, so up to 256 colours. And the data that it gives you is not the colour data, but the palette index data. I don't know if you know how a palette system works, but instead of storing the colours in memory, you just store a number from a lookup table, which then gets translated into the full RGB. So you can have 256 colours stored as 1 byte each, but that 256 colours comes out of a palette of 16 million. So you've got access to all 16 million colours, but only 256 of them at a time. And it's that 256 index that gets fed out through here. So theoretically, I should be able to interface something to this and decode the data as it comes out, then look that data up in my own manually created palette, because there's no way you can find out the palette from this. So you'd have to manually create the palette, remap those index numbers to the right colours, and then output that on, say, a HDMI or some other channel that I can then capture from. So that's my plan. Whether it'll work or not, I have no idea. But the first step really is just to look to see exactly what does come out of this connector. For that I have my trusty, or is it rusty? Where's the right page on here? There we go. My trusty old, well, I say old, I've only had it about 2 weeks, 486, which is a mass of wires. But it should, hopefully, give me a video signal that I can actually probe with my logic analyzer. So let's just look at the graphics card that's in here. This is a Cirrus Logic GD5430, I believe, in here. It's a pretty basic card. I think it's 256 kilobytes. So it can't do high resolutions, it can't do lots of colours, but it is your sort of basic card of its time. I mean, I'd like to replace it in here with a something like a Trident 9440 with a meg of memory. At some point I may do, but it has, as all these cards seem to have, the feature connector. But again, as you can see, we have the main chip, we have the memory, we have the BIOS. That's all the chips on here. There is no external RAM DAC, and you just don't get external RAM DACs at all these days. So it's down really to intercepting just those indexed palette colours. So the first job I need to do is work out which way around this connector is. It's in all the images that I've seen, all the diagrams I've seen, it's always been indexed with a key. Let's bring back here so you can look at my ugly mug. And there we go. That's the supposed pinout. You've got 8 bits of colour data. You've got the DAC clock, which is the pixel clock, which is 1 clock per pixel on the screen, which is absolutely perfect for what I need. The DAC blanking, which defines the period that's actually displayed on the screen. The horizontal and vertical sync, so you know where on the screen you are. And lots of ground and a couple of select pins Z4 and Z5 on here. Select internal defines colour pins as outputs when high. The adapter pulls this signal to 5 volts through a resistor and defines sinks and blanking pins as outputs. The adapter pulls this high through a resistor. So what that does is, when in normal operation those two pins are held high and the video card just operates and outputs the data through this connector. When the Z4 pin is pulled low, the colour pins become inputs and the graphics DAC, the RAM DAC, will start outputting whatever data is placed onto those pins. So you can intercept the video signal at a specific point on the screen and output your own data through that connector. That's used for things like MPEG decoders and that sort of thing, where it wants to effectively overlay the graphics. It sort of inserts it into the video stream using that. And similarly for the blanking pins, the sinks and blanking pins, when it's high, basically the card is generating all the timing signals. When it gets pulled low, all the timing signals come from an external source, which is great for synchronizing the graphics card with, for example, a TV broadcast signal or something like that. A system known as, in the Amiga world certainly, as Genlock, where the card is synchronized with an external source, so you can overlay the card's graphics on top of a live video signal, for example. So, people sending me messages. Is this of any interest? No. Just emails coming in? No. Reply to this one a moment. So yes, that's my plan, is to experiment with that. So yes, the first thing I need to do is work out which way around it is, because if we bring this image up again, you see that the last pin on the Z row is missing, which would normally be the index to say which way around it goes. But on this one here, let's switch back to this view. This one here, it has a different pin missing for the index. And this one here has all the pins present, no index. The same with this one, there is no index pin. Fortunately, this has the pins numbered. Not all of them do, but this one does, so I can see which is pin 1, which is this end. Which means, hopefully, I can see, yeah, that looks like it's going to be the right way around. Let's get a bit more light on the subject. If I can focus in on this. I'm not there. There we go. Come on, focus. Focus. Thank you. We can see the 8 data pins coming in on the left-hand side of that connector along the top row there. I'm assuming those are the 8 data pins. They're looking like they should be, coming straight from the chip. So I'm hoping that is all numbered the same way as that image. I mean, it's supposed to be a standard. So theoretically I should be able to connect that up to a logic analyzer and see the actual signals coming out to confirm that it's working, as I believe it is. So for this, I'm going to use the DreamSource Lab DSL U3 Pro 16, DS Logic U3 Pro 16 channel logic analyzer. This is an absolutely awesome bit of kit. Comes with a whole host of adapter cables, and this can go up to 1 gigasample a second, I believe it is, over USB 3. So that should give me enough bandwidth to be able to monitor the signals. And hopefully I can just hook these cables. It does also come with little clips as well if I need them, but hopefully I can just hook these cables directly on to this header for monitoring. So let me see if I can bring up the image on here. Okay, let's shrink it down a bit. And we'll pop it down there, I think. Okay, so you need the 8 data pins first. And for that, these wires are all colour coded. And it matches the colours of the channels within the software. So we want to start off, and the colour coding is all the sort of standard rainbow colour coding. So we shall start off with this set of wires for grey, red, brown. Grey? No, is it? Hang on, no, let me think. Let me just check these. Because they are different. They do have slightly different arrangements. For this, I think I need to bring up the software. Just check that I get the colours right. Nice. Grey, red, grey, brown, red, orange is the first block. Grey, brown, red, orange. So this is the first wire to use. Grey is data 0. So that needs to go to, if I can read that, pin Y1, which would be here. Perfect fit. Then the brown one. Okay. Then red. And then orange. And I've got the wrong glasses on for seeing this at the moment. What have I done with my other glasses? There they are. Oops. Come back. OBS. Okay, that's better. I can read that now. So it also says here Y13 1, 2, 3, 8, 9, 10, 11 are ground. Was 1, 2, 3. Y13 Z. We've got 1, 2, 3, 4, 5, 6. There are 8 grounds there. That's good. So Z1, 2, 3, 8, 9, 10, 11. So I'm going to ground these on Z1, 2, 3. Because it's convenient. Okay. Z1, 2, 3, 8, 9, 10 and 11. I don't think I'm going to ground many more of these. But the next block is yellow, green, blue, purple. So here's yellow, green. Find this wire. Yellow, green, blue, purple, yep. So yellow, green, blue and purple. Okay. Actually, I will ground the rest of these, I think, if they will reach. So that was Z8, 9, 10, 11. There's 13 pins per row, so 13, 12, 11, 10, 9, 8. Let's keep these in order if I can. 9. No, actually, I shan't do the orange one. I shall sacrifice the orange one. 13, 12, 11, 10, 9, 8. Then the green. 9. And then that blue one, 10. That'll do. I shall not worry too much about the others there. There's one from each cluster is not connecting at the moment. Right, next goes, it repeats, so we've got another grey, brown, red, orange. Grey, brown, red, orange. Now here we need the DAC clock, blanking, and the two sync signals. So Y, 9, 10, 11, 12. So it's continuing along from these, with the grey one first. Grey, then brown. Then red, then orange. Oops. Come on you go. There we go, red and orange. So we've got Y13 as a ground. I shall connect... I want to connect the one that's on Y10, that's the brown one. I want that one to have a ground, because that's the Y9, sorry, that's the grey one. I want that to have a ground because that's the DAC clock. So that can go onto there. Then we've got 10 and 11, or just 11 available, so I shall just slip on. The horizontal sync is the next fastest signal, which is red. I shall ground that one. Okay. I think we're wired up well enough there. Enough signals connected, and there's enough grounds there. Right, I'm just going to take out my network card a moment, just to give a bit more room. Although, do I need... No, I don't actually need to, because it goes this side of the card. I think, doesn't it? Yes, it does. That can stay in. Okay. So I'm now plugging in the card. Right. We're in. Then Dream Source Lab. Let's get these in the right order. There's no markings on them to say which is which is a bit annoying, but we can manage. This is the third bank. These just plug into these little, lots of little pinholes here, if it'll focus. Come on, focus, there we go. Lots of little pinholes with an extra slot underneath, which then mates up with the piece of circuit board that's underneath the connector. So you can't physically get it in the wrong way round. So that's that one in, and the next one is this one, goes into there, and this one into here. Okay, that is plugged in there. Now I need the USB cable, and this is where I find that for some reason I've left the USB cable out. There it is, I've got it. It's USB 3, so it's a USB-C connector at this end. In it goes, any old way up, doesn't matter. Right, now I shall turn on the computer. Everything gets loud. Drink. That should be generating a signal now. I don't have the monitor plugged in, but there's the beep. But what I do have here is the DS View software. Let's just adjust the window size here a bit. Come on, there we go. This is based on SIGROC, which means it works on Linux, Windows, OS X, everything. It's already detected we've got the DS logic. Why does it keep beeping? It must be in a boot loop or something. But that's fine. I don't mind that at the moment. Doesn't like the logic analyzer being connected, probably. Actually, no, I will just plug in screen a moment and see what's coming up. It's displaying properly. It seems to be, yeah, it's boot looping at the moment. I don't know why. Have I got a? Let's take the floppy out. Starting MS-DOS. That's better. It was whatever was on the. I've got a GoTech in this at the moment, and had a memory key in there, so it was trying to boot off a floppy image, which was just messing it around. I mean, can't really show you what's on the screen, but at the moment it's just my boot menu for DOS. So, right, let's have a look. On DS View, these are the 16 channels, but I don't need all 16, I only need 12. So I'm going to switch to 12 channel mode, which ups it to 250 megahertz whilst streaming. It does also have a buffer mode where it can do all 16 channels at half a gig or 8 channels at a whole gigahertz. I want 12 channels and I want to stream it. So switch to 12 channel mode, stream mode, threshold. I'm going to increase the threshold level actually because it's going to be TTL, so I'm going to go 2.9 volts for TTL. Filter targets, one sample, no, I don't know what that means. Maximum height, don't know, something to do with the display. Using external, it has the option of using an external clock, which might be a very useful thing because I might be able to connect that to the DAC clock and have that as the sampling source. But for the moment I'm just going to do a raw sampling. Okay. I'm going to need this pretty quick. So I'm going to go 100 megahertz. That's more than the VGA pixel clock, which is 25-ish, I think, megahertz. So that should be plenty more than the actual signal. You want to have the sampling frequency to be at least twice the maximum frequency you want to sample. It's called the Nyquist-Shannon theorem, that is. You can look it up on Wikipedia. But basically you need to, if you think about it logically, if you've got a square wave that's going up and down, to sample the fundamental frequency of that square wave, you have to sample twice within one up and down. Once on the up, once on the down, to be able to get the timing of the whole thing. So yeah, you have to sample at least twice the frequency that you're interested in. So this should be 4 times the frequency, which should give me a good bit of variance. Excuse me while I just choked to death. Okay, we can also on here, on this left-hand column, label the signals. So I'm going to do that. I've got colour pins C0 to C7. Just makes it easier to remember which trace is which. C6 and C7. Then we've got the DAC clock. Then we've got, let me just bring the image up again, get the order right. DAC horizontal, vertical. So it's blanking horizontal, vertical. Okay. And so BL, H and V. Okay, let's now just do one frame lasts for hardly any time at all. Let's do 50 millisecond sampling at 100 megahertz. Go. We have data. And it started absolutely hammering it down outside and the window's open. Oh, and we got lightning. Haha. Let me just close the window. We have a thunderstorm. I do love a good thunderstorm. Right. We have data showing. That is excellent. Now let's zoom in on here. I'm using the trackpad on my laptop actually here. It's not very friendly for this. Actually, let me find a proper mouse. Somewhere here I have my trusty IntelliMouse. I had it in my hand earlier on while I was sorting the desk out. That's my old Wise. Where's my IntelliMouse gone? It's not over there. It's not down here. No. Hello, IntelliMouse. Where have you gone? Ah, there it is. Found it. In my opinion, the IntelliMouse, this is the version 3A, 3.0A. This is one of the best mice ever made. I mean, I don't like Microsoft. I'll pull no punches there, but Microsoft, I always say, cannot make a good operating system, but they can make a good mouse, and this is the proof. This mouse is the best mouse ever. It's comfortable, it's reliable, it works really well, it's it's just a really good workhorse of a mouse. So let me just plug this in so that I can get, there we go, proper mouse control now. Okay, so what do we have on this display now? Well, we have the pixel clock, which is running currently here at 33.333 megahertz. Not bad, not bad. It's, as you can see, because it's not an integer factor of 100, it's a bit... Hello. I was saying that this mouse works well, it's just decided to be a bit iffy, but that might be the connection on my laptop actually. Or it might be the cable. I have actually replaced the cable on this mouse. I've had it so long that I've actually replaced the cable on it because the cable died. So the cable is actually an inferior cable now. Okay, as I was saying, yes, because it's not an integer factor of 100 megahertz, it's not perfectly even on the display. It's some wider than others as the sampling sort of shifts in relation to the actual signal. If I did a higher frequency, I would get a more accurate representation. Or if I did a multiple of 33.333 megahertz, I would get a more accurate representation. But that's fine. That does the job. So that is one clock for every pixel on the screen. Then we have the blanking period. The blanking signal is basically low when you don't want anything displayed and high when things are being displayed. So if we zoom out for a bit here, this is one line of video data from there to there on the screen. And then you've got the horizontal sync, which occurs within the blanking period. And on an ordinary VGA signal, the blanking period basically turns off the video signal. So the output is only active during the actual display portion of the line. So let's zoom out a bit more, and we should see. Here is one frame of image. So if I can get the whole thing on. Yep, I can just get the whole frame on. We've got a pulse at the beginning for the start of the image, basically the vertical sync to say this is the beginning of the screen, with a nice long blanking section where there's no image being displayed, and then the image starts here. Then we have scanning down from the top of the screen each individual line of the display with data on. Then there's a big long blank, and then data at the bottom, which is exactly what I'm seeing here. I've got a menu showing. I wonder if I can get it on sort of on the screen for you. Let's get the right mouse, and if I spin this around, there we go. You can see the screen there. So I've got an MS-DOS startup menu with 3 entries on it and a line of text at the bottom. Switch back to the capture. We have the menu and its entries and the enter choice. That's the MS-DOS 62 startup menu. That's the underline. That's the Windows, and it's got extra bits on here because it's highlighted. That's the attribute data, the different colours. And we've got minimal DOS, full DOS, and over here it will be enter a choice, and then down the bottom here is F5 equals bypass startup files, F8 equals blah blah blah, message at the bottom. So that looks exactly like I was hoping it would, which is remarkably useful. There's no colour information there, just pure index. So I've got currently a black and white display, but with highlighting on it. So we've got 3 bits. Ooh, nice rumble there. 3 bits for white. Oops, come back. It has a habit of running away with you sometimes, this program. So yeah, for white we've got basically 7, which is what you'd expect for white, basically. If you think of the ANSI colour schemes and things like that, 7 is white. Then if we come along here to where the highlight is, on the word Windows, zoom out a bit so we can see, where are we? Here we go. Here we then get extra data. We have a white background, so we've got solid white here with bits, oops, come back, of brighter white within it. So we go from 7 for the background to, what would that be, 7, we've got 1, 2, got 2, 4, 1, 2, 4, 8, 16, 32, so 64, so that'll be 63. So we've got between 7 for the background and 63 for the foreground, which is bright white. I could take all this data, export it as a CSV file, and then write a little script in PHP or something which would take all this data and render it to a PNG file. And you should end up with exactly what is on the screen here. And that, I've done that many times before with other display systems. So let's zoom in on this a bit further so we can see the clock. So if we're going on the vertical edge, we've got a line here going across the screen of a white pixel, a white pixel, a white pixel, a black, come back. And every time I touch the right mouse button it just zooms right in and I lose my place. It's a bit annoying that on this software. Yes, so you've got a white pixel, a white pixel, a bright white pixel, a bright white pixel, a bright white pixel, a white pixel, etc. Oh, come back. That storm is getting pretty close. I hope it doesn't cause a power cut. Until we eventually get here, white pixel, black pixel. So the data that I'm getting here is exactly what I was expecting, which is good. So for ordinary DOS text screens, it's spot on. I wonder what I would get in a CGA mode. Let's switch to minimal DOS and load up an old CGA game. Hey. Where are we? There we go. Alley Cat. Classic old game. I don't think I can shut this up. So I'm just going to reach in to the computer itself and yoink out the speaker. Okay, so I've got Alley Cat running now, which is in CGA mode, which is 4 colours basically. You've got black in this. Well, it's got multiple modes for CGA mode, but this one is black, pink, or black, magenta, cyan, and white. Oh, it's just gone into. Let's get into the game. Okay, so let's run a sampling on this one and see what we get. Now we're getting just 3 lines of data. Our clock now is running at 12.5 megahertz, so it's much slower to be expected because it's half the resolution, if that. We've got largely a pink background here. So if I come to the start of a frame here, let's put a marker in. Okay, here's the start of the frame. Now this, I notice it's outputting. Ah, here we go. Started. Yeah, I'm not zoomed in enough. Oops. Okay, so this is the start, first pixel of a frame. That's a magenta background, which is 101. Which. Now I wonder. I was expecting this to be outputting basically just 2 bits of data for the colour, because you've got 4 colours to choose from. That can be represented just as 2 bits. Sorry, that way around. If that's represented, I've just realised you can't see what I'm doing here. Switch back to capture. Where's it gone? There we go. Yes, we've got. I was expecting it to output 2 bits of data, and then that to be looked up in the palette to represent the 4 colours. But it looks actually like it's being output as 3 bits of data for red, green and blue. For the magenta background you've got red and blue, or it might be blue and red, it's hard to tell. Which means when it's in the other CGA modes, it should be giving the actual colours out again. I wonder. Let's reboot, because I've got another game which alternates the palette. Because if the CGA ones are outputting the actual colour, not the index colour, as a 3-bit value, then that means I don't need to worry about manually switching the palette when the mode changes. I've lost my screen now. Come back. Okay, into minimal DOS. Okay, this is Livingstone. A bit of a strange game. It's sort of your platformy kind of thing. But this is in the red, green, yellow, black mode at the moment. So I'm just going to run a capture on here. Right, interesting. This gives a completely different set of values. Where are we? Capture. It's still 0 for the background, of course, for black. But then we've got this will be red here, I suspect, which is giving me what 2, 4, 1, 2, 4, 1, 2, 4, 8, 16, 18 for red. So it looks like it's mapping it to a fixed palette for the CGA emulation, I suppose it would be, wouldn't it? I wonder. Let's just look up online. The VGA palette. 18 would be... Is it going to be 18? Let me just check that. I've got 1, 2, 4, 1, 2, 4, 8, 16, 32, 64, 128. So that's 16, 17, 18, yes. Actually, tell you what, let's make life easier. Let's do a decode. And I want to do a parallel decode for this. Okay. And where are we? Okay, parallel. Clock, I want to have declock. The colour lines is the data lines. Colour 4, colour 5, colour 6 and colour 7. And what this will do, clock on the rising, what this will do is it'll go through the entire trace, and on every rising edge of the clock, which is the DAC clock, it will read these signals and convert them into a hexadecimal value. Except it just crashed. Great. Let's try loading that again. I've lost all my settings now. Okay, let's put everything back in again. If this will connect. Come on, keyboard, connect. Come on. Problem with Bluetooth is half the time it just does not want to work. Okay, let's go into settings and go into pairing mode. Oh, it's connected now. Typical. Go into settings and it connects. Okay, so C0. C1. It would be nice if there was a way of quickly switching between each channel for entry. If you pressed, it'd be nice if you pressed enter or tab or something, it went to the next one, so you could rapidly go through instead of having to reach over for the mouse every time just to click the next one. C6, C7, declock, blanking, horizontal, vertical, and options, and 12 channels, 2.9 volts, okay, and actually I can, for this screen mode I can bring it down a bit actually, reduce the amount of data to 12 megahertz, so let's go for 25. 25 should be good, and we shall run for just a couple of milliseconds, 20 milliseconds, and start. Now I'm going to save this. Feature CGA. Okay. Right, let's try doing the decoding again. Decode, parallel, add, clock, declock, 8 data bits. And OK, and it's crashing. Great. OK, I'm not quite sure then what I can do with that. Let's run it from here. And I want, what did I call it? Feature CGA.dsl. What's it doing when I do parallel, add, declock, 0, 1, 2, 3, 4, 5, 6 and 7. Segmentation fault. I thought it probably would be. Right, there's not a lot I can do about that at the moment, unfortunately. So, where are we? I'm going to have to just do this manually. So we've got we've got 2, 4 and 16. So that's 18, 22. 22 in hexadecimal. Well, actually, it's easier to work in this, isn't it? So we've got 1, 2, 3, 4 traces and 4 traces. So we can split that in half. So we've got 0, 1, 1, 0, which is 4, 5, 6. That's 6 and 1. That's 1, 6. 1, 6 on the VGA palette apparently is grey. I can't see that myself. Let's just try something else. CGA emulation. Oops, wrong keyboard. Switch back to Wi-Fi 1. Okay, CGA emulation palette. Full CGA 16 colour palette has 16 colours in it, obviously. It's a 16 colour palette. But that's for 16 colour mode, which is used mainly for text or very low resolution. Of course. No, yeah, no, hang on. Because you've got 8 colours. Then you've got the same 8 colours in high intensity. So you've got 3 bits for the 8 colours. And then it should just be 1 more bit for the high intensity, which I would expect to be on C3. But I'm seeing that on C4. I'm wondering actually if... have I got these connected the right way? I'm on grey, brown, red, orange, yellow, green, blue, purple. Yeah, that's the right way around. Yellow, green, blue, purple. That's correct. So yes, it's the right way round. Let's just bring this so we can see the whole thing. So the colours that it's giving me it is different colours for the different modes. Let's wait for the mode to change. This is currently in. Oh, and let's switch to there. Oh, we've lost. Okay, we lose all the settings when we switch over to. Oh, nice bolt of lightning there. When we switch over to DS Logic, we lose all the settings that we had up before. It would be nice if it would. Oh, sorry about that. It'd be nice if it would keep the settings from the file you've loaded. There's a few things about this software which I don't like. You lose all your settings. 25 megahertz. Let's do a longer sampling actually. Okay. Sampling for a whole minute here. We're on the green, yellow, red palette at the moment. That's palette 0, that's called. And it's... I'm sure this one changes depending on where on the game you are. Go on, change palettes. It's not doing it. No. So for this colour scheme, it's bits 1, 2 and 4. If I reboot and go into Alley Cat, come back display, stop switching over. Okay, stay on VGA please. I mean, I could probably knock up a quick DOS program to a quick basic program to switch modes at will. Okay, games, old, Alley Cat, and then I do a sampling on there. This is using bits 0, 1 and 2. Okay. So for magenta background, I've just noticed something with this clock. We're getting bursts of clock here, but that might just be the sampling actually. If I go to a faster speed, yeah, it's just the sampling. Right, magenta, there's just text on the screen at the moment saying, do you want to use a joystick? So if I zoom out, this is the text. So magenta is 1, 2, 4, 5, which on the mode 4 palette 1 color 5 is magenta. That's correct. Okay. Don't know how we can actually get out of Alley Cat without rebooting. I think I've killed it. So I think maybe on this card it's got some of the bits around the wrong way. I don't know. Let me just check. C0, 1, 2, 3, 4, 5, 6, 7, that's right. So I'm just wondering if on this card they've got the bits twiddled slightly. I wouldn't have thought so. Because let's look at... Go back into Livingston again and do a sampling. On this one, I would expect if it was just using the palettes, to be giving me on here 2, 4 and 6 for the colours, or if it's in high intensity 10, 12 and 14, which makes sense with the bit 0 being always low. But I would expect bit 3 to be toggling, not bit 4. Because on the screen, I know you can't see the screen, but we've got the Livingstone logo is black background, and then it's red and yellow. So you've got red and yellow adds in that bit there, which red is 12, yellow is 14. So adding 2 into it makes red yellow. So that bit there really should be there. Orange and yellow appear to be backwards. Interesting. That's strange to say the least. Unfortunately, my other graphics cards are too powerful for the 486. So I can't test a different card in here. The Voodoo 3 doesn't work on it, the Matrox doesn't work on it. Which is a shame, because my original plan was to use the Matrox G450, which would be a very nice card for video capture, because it has DVI on it, which could then go directly into my HDMI capture card. But unfortunately, it doesn't work. Whoa, nice lightning. Unfortunately, it does not work on the 486. I think it's basically too new. It needs at least a Pentium. Probably a Pentium 2 or 3 maybe. So I'm having to resort to other methods, hence this. So it's odd that it's giving that... Oh, I keep on hitting the microphone. It's odd that it keeps on giving the wrong output here, or not the output I would expect. But that might just be a quirk of this specific graphics card, or this specific chip. It's the GD5430. Let's see if I can get a data sheet for it. Yes. Okay. What do we have? Pixel clock programmable to 135 megahertz. Nice. Anyway. Yeah, we have in the block diagram. Let's have a block diagram. host interface, VESA local bus, PCI bus. Pixel bus, bidirectional pins. These pins are inputs. Well, they can be outputs directly. These pins can be connected directly to the corresponding pins of the feature connector. So that's P7 to 0 on here, which is right. I'm going to see if I can just add window capture. There we go. Right, you can see what I can see now. Right, yes, the block diagram. We have the feature connector goes in here, basically. That's the P7 to 0 pins, which are, as it says here somewhere. No, I've lost it now. There. The pixel bus. So I should actually theoretically be able to trace those through to PCI bus. Somewhere on this massive chip. Where would they be? Here we go. 0, 1, 2, 3, 4, 5, 6, 7. They're all in order. So I wouldn't have thought it would be twisted around on the header. So it must be this is all graphical, isn't it? I can't search it. It must be internal to the chip that it's doing that twisting around then. Do we have an index? No, we don't have an index. Yes, we have an index. Palette DAC might... Oh, that's just a functional block. Let's take a look though at 3 to 11, page 339. 19, 39, there we go. Can be, oh. Configuration tables might be in here. So, horizontal frequency, pixel frequency. Mode 4. 4 colours. 320 by 200, 12.5, that's exactly what I'm seeing. Registers. No, there's nothing really that tells you what the palette is. which is a shame. So basically we have, let's bring this back again. There's 4 bits of data. You've got 3 bits for the colour, and then you've got an extra bit here for effectively high intensity. I would expect that bit to be on there, but it happens to be on there. That may be intentional. Well, obviously it works, so quite why we're seeing it on. They've chosen to have it on that bit, I don't know, but it's probably something to do with how the palette DAC works. So this now is something which could actually be captured and interpreted. And I understand now just how it works, but I just want to just have a look at a higher resolution or more colours. Actually, I want to look at more colours rather than higher resolution, because I have a theory this should be useless in high colour mode, because it's the colours that go into the palette. So either in a high colour mode, either we'll get nothing because there's no palette, so it's just not going through this system at all, or we might get the lower 8 bits of the 24-bit graphics. So we might just get blue, for example, just the blue component possibly. Or we might get just the red component, which won't be particularly useful, but it'd be interesting. It would mean that we could run in a monochrome mode or something, and then capture it and then reconvert that back to monochrome. Right, just going into Windows 3.11 here. Alright, let's bring that up. This is going to be slow, isn't it? I haven't got my network connected, so it's going to be timing out on the network here. Let's plug this in. That might speed things up. There we go, we're into Windows. Right. I need my other mouse now, which is another IntelliPoint. This is tangled up in cables, because of course, why wouldn't it be? Okay. This is the older mouse type of IntelliPoint. Just as comfortable, just as reliable. This is decades old and still working well. Let's just log in. Okay. And we want... where is it? Can't see because of the laptop. VGA utilities. Currently we are running in 65,536 colour mode. Let's switch to 640 by 480 and 16 million colour mode. In 16-bit mode, the 65535 colours, apparently it uses a 565 encoding scheme. So you've got 5 bits of red, 6 bits of green, 5 bits of blue in a 16-bit address space. Is this going to reboot or not? No, it's not. Let's reset. And switch back to VGA again. If it will. Come on. There we go. Oops. What did I just do then? I pressed a button. Come back. Okay, into Windows in 640 by 480 at 24 bits. Full colour mode. See if we get anything. Eventually. Right. Not enough memory to convert all the program icons, I don't care. I've got a memory upgrade coming. It's only got 8 meg at the moment. I'm going to be doubling that hopefully soon. Okay, I need to find the right mouse. I've now got 3 mice on the desk to choose from. Let's take this up to 250 megahertz. This mouse should let me go to here. And start, done, okay. We're certainly getting data, we're getting all 8 bits of data. At the start of a frame, actually what speed is the clock on here? 83 megahertz. That might be a little too high for me to sample with a small microcontroller. Stop doing that, small microcontroller. So it may have to be something meaty like the Pi. So we have, from the start, we have all sorts of weird colours here. This is the grey mottled background. Then we have, that's my taskbar thing there, isn't it? My office bar. What I think I should do is, let's take the window and bring it up to the top left. So I have blue at the top of my screen. There we go. So I've got the Program Manager title bar right at the top of the screen, so it should be just plain blue at the top. And back to capture, and I only need very brief capture. Okay, so we have we have solid blue, and not sure actually about what we're seeing here. Actually no, what am I doing? I'm looking at a random scan line, it could be anything. What I need to do, let's set up a trigger on here actually for the vertical sync. A rising trigger of the vertical sync. Increase the time a little and start. There we go. That's the beginning of our frame. So we're seeing blue, which is just bit 7 being on. Then we have white for the Program Manager text, which then turns everything else on. Weird. Then we have the bar there. And then the greys. Okay. Now this is not quite as I was expecting. Or is it? Maybe it's reversed. Because we've got quite a dark blue. Actually, have we got some form of... Not sure we've got a program on here for drawing, have we? There's no paint program on here, is there? Well, I've got all sorts of things on here. Actually, there will be something on here. Let's just load up Office. And arrange window cascade. Okay. Let's bring up PowerPoint. That'll do the job. And we want... Yeah, there we go. So you can sort of see what I'm doing. Blank presentation. Okay, whatever. Delete. Delete. Slide background. Change colour. Red. Okay. Apply. Insert new slide. Blank. Slide background. Change colour. Green. Apply. Hello. Desperately need my memory upgrade. Barely able to function with 8 meg. I think it's just crashed. I am actually wondering if this computer has got a problem, because it does like to crash. It might just be a memory problem. Might be a lack of memory, might be faulty memory. But I've done a few memory tests and they've come back okay. And CPU tests, they've come back okay. Everything seems to be okay. But it does like to crash. Oops. Not used to having this microphone up here, I keep bashing it. Let's try this again. This time I won't make more than one slide. Okay, where were we? Microsoft Office. and PowerPoint. Blank presentation, blank slide, slide background, change colour, let's go for solid red, apply, and I can't remember how we use this now. Slideshow, there we go. Okay, solid red screen. Now we do a capture on here. Solid red is giving us a 0, 0, 0, 0, 0, 0, 0, 0. So there's no red component in the data. We change the background to blue. I don't know how blue this is. Let's go more colours. Okay, so red 0, green 0, blue 65535. Okay, that is as blue as it can be. View slideshow. We have a blue screen now, and start. We are getting okay, we're getting half blue, half black. Alternating blue, black. Oh, hang on. I wonder. Oh, that could be interesting. A thought has just sidled its way into my brain and nudged me. Let's have something odd like orange. View slideshow. An orange screen now. Might explain why the clock is so much higher than I was expecting. Yes! Oh! Oh, indeed. This might be even better than I was hoping. We're seeing a repeated pattern here. With this on one clock, next clock this, next clock this. Repeat back to that for that clock, etc. I think we've got 3 times the amount of data here. I do indeed. I think we've got interleaved 8 bits, red, green, blue, red, green, or blue, green, red, blue, green, red. Which is why the pixel clock here at 83 megahertz is so much higher than I was expecting. Because if I look at the data sheet, 640 by 480, if I can find that page again, 640 by 480, 31.5 at 72, or 25 at 60. for 640 by 480. Although we're in, let me just get the 640 by 480 in full colour mode. 16 million, 640 by 480, yeah. We might have a pixel frequency of 25 or 30 something. 30 something would make sense. It depends on the refresh frequency, 60, 71 or 75 hertz. Or 60, 72, 75 hertz. So we've got, if we're running at 31.5 pixel frequency, that would be about 93, 94, 95, yeah. 93.5 megahertz. And I'm seeing 80 odd here, varying around 80 odd. Right, so it looks like in full colour mode we are getting full colour pixel data at 3 times the rate, interleaving the 3 different colours, which would be absolutely brilliant, because then I don't need to worry about mapping colours and palettes, and I can actually get true colour output from it and sample it. And right, now I wonder what would we get in 16-bit. Which will that output 2 bytes? Where are we? VGA. Come here. VGA utilities. VGA mode. Let's change into same resolution. So that's 60 hertz we were running at. So that should have been 75. Yeah, 75. That would have been about right. Let's switch to 16-bit. Needs to restart Windows, which will fail. Do we get double the clock frequency? Do we see 50 megahertz clock for a 25 megahertz pixel clock? Currently I'm seeing 25 megahertz, but it's currently in low res mode, or low color mode, just for the logo. Okay, yes, that's just increased to 50 megahertz. So I will now be getting doubled data, 16 bits of data as 2 8-bit slices. Right, that's interesting. But then now, of course, it begs the question, how can I tell? How can I know what... I can work out what resolution I'm running at by the timing of the sync signals. That'll give me the... theoretically, because I can count the number of lines easily enough. and I can time how long a line lasts for. But I can't know how many clocks per pixel there is. I don't know whether I'm running in 640 by 480 or 1280 by 480 or 1280 by 1024 or what. If I just try counting the clocks, I've got no idea. I wonder, actually, no, the blanking period, or the sync period, vertical sync is exactly 2 lines worth. Horizontal sync could I count the clocks? What I'm thinking is, can I count the clocks within the horizontal sync and calculate from that the number of clocks per pixel? Interesting possibility. So we've currently got a 3.828 microsecond pulse for the sync. Let's switch to 800 by 600. Now remember that it's a width of 3.828. 3.828 with 2 clocks per pixel. Okay, I am now in 800 by 600. And now, okay, this seems to have inverted. That's now 3.224, so it's almost the same, but it's inverted it for some reason. But anyway, that's not much of a change. So I can't really get the resolution from that. I can get the resolution from the width of that at 23, well, a frequency of 37 kilohertz, 37.89 kilohertz, which is 60 hertz refresh. 37.8 is the horizontal frequency for 800 by 600. But then you've got 37.9 is the horizontal frequency for 640 by 480 at 72 hertz. So no, I'm not sure I can easily calculate. When there are so many options of frequencies that can come out that give such similar results. I mean, I can have manual configuration, I guess. It's no real hardship. I mean, it'd be nice if it automatically changed sampling and everything, but the majority of my capturing of this is going to be old DOS games, which are probably going to be working in VGA standard modes or CGA modes. For VGA modes, there is a complication that you have a palette of 256,000 colours which you can pick from. Mode 13, 320 by 200, can have 256 colours on the screen from a possible 256,000. I'm wondering, is that mode going to give the indexes? Or is that going to give the colours? I am not sure. And I'm not sure I've got a game on here that would work with it, have I? Oh! I wonder what Doom would do. Not sure what mode Doom runs in, but it's certainly more than just a few colours. Okay, this is the Doom logo showing on here. Which is a 12.5 megahertz clock. 12.5 megahertz must be... I suspect that's the 256 colour at 70 hertz refresh frequency at 320 by 200, isn't it? Yes. Those are the standard VGA video modes. I can't see Doom using a non-standard video mode. Because the non-standard video modes require a driver really to use. So this is a standard VGA video mode. It must be in 256 colour mode, which means it must be using palettes, I would think, unless... No, I would need... the 12.5 megahertz clock. That's not doubling or tripling anything there. So that must be giving me indexes. In which case, this mode may be pretty useless. Doom does seem to have its own palette. The PlayPal lump is a set of colour palettes the Doom engine uses to set the main colours for all graphics, including full colour fades and tinting effects. 256 colours, colour map resource, so yes, it does use its own internal palettes. And if that is as it looks to be index data, then I would have to map to this colour palette. Which is fine just for Doom, but of course that's specific to Doom. That suddenly all gets a lot more complicated. Right. There is no way to extract the colours from this when running in a palette-based mode. However, I'm wondering if Doom captures or not. So I don't have to use this for all video modes. I can chop and change. Let me just connect up. If I've got a power cable here. Do I get anything on here from Doom? No is the answer. This is why I want this system really, because this converter is rubbish. I do have another one coming, a different make of the same sort of thing, but that's coming from China and will take months to get here. No, that does not capture. Which is a shame. So, how can I do this then? I mean, I can have it in software, map it. That's not a problem, as long as you know what the palette is. For Doom, the palette is documented, which is good. I assume the same palette or similar palette for Doom 2. For other games, who knows? And no doubt a number of games will use tricks that are used across the board in 8 and 16-bit systems of changing the palette at will. So, there's not a lot really I can do for those, other than manually loading a palette to map the indexes to. However, that's good results so far, and I'm now in a position to start thinking about actually doing some capturing. That's not something I'm going to do tonight. I'll need to, for 85 megahertz, it is beyond the realms really of a PIC 32. It's probably beyond the realms of an ESP32. It's more than likely beyond the realms. Well, might be capable of doing it with an RP2040. The problem with the RP2040 is, that's the Pi Pico, is getting the data out of it again. Because the PIO in it, the programmable input-output system, it would be absolutely perfect for this, but it only has a USB 1 connection to it. So although it could capture a frame, I can't then do anything with it. I can't get it out onto the computer fast enough. The advantage of using, say, a full Raspberry Pi or a Pi Zero is it has a built-in HDMI output. Don't want that on. Right. So yes, I've made good progress there with it, probing it. Now to work on capturing. So yes, I'll probably use a Raspberry Pi, because that's running fast enough, certainly at 1.8 gigahertz, is it? 2 gigahertz, something like that. Multi-core. So the problem with that is it runs Linux, which kind of gets in the way of real-time operations. It's constantly doing things. So it would want to be certainly interrupt triggered on the clock. The other option is, because it's just a straight chunk of 8-bit data, possibly I might be able to use a PIC32, one of the MZs. It may want to be one of the ones with a built-in 32 meg of DRAM though, in order to store an entire frame. Because what I'm thinking is, actually I might be able to do it scan lines. If I trigger on the horizontal sync signal, or maybe the horizontal blanking signal, and use DMA on the parallel master port of the PIC32 to read the data in and store one line of data, one scan line of data. Then while it's reading the next scan line of data using DMA, it could be outputting that current scan line of data through high-speed USB 2. It's possible. I might be able to capture this reliably, even with the 85 megahertz, using DMA on the PIC32. I'm not up on the ESP32 enough to know about being able to do DMA from an input port. ESP32 would be quite nice, because then I could connect it up using Wi-Fi, possibly. Although USB is fine. Yeah, in fact, USB might be better because it's less latency. I could even possibly get the PIC32 to present as a webcam, which would be useful. Although programming that's tricky. What are the other options? So the other option is the Raspberry Pi or the Pi W, which has the advantage that it has its own HDMI port built in. Then that can just go straight into the HDMI capture card. But as I say, that runs Linux and that kind of gets in the way. So I'm in two minds whether to use a microcontroller or an SoC. Single board computer, system on chip, or a small microcontroller. When I say small, these PIC32s with 32 meg RAM aren't small. They can run Linux on them just about, though you wouldn't. So I'm torn really between the two. The microcontroller would give the more reliable operation, but getting the data out would be harder. The Pi would be harder to get the sampling right because you're fighting with an operating system, but it could be rendered directly to the frame buffer. So I don't know. I think probably, at least to begin with, the Pi is going to be the easier option. It'll allow me to visualise what I'm sampling a lot easier. Although, no, I was thinking I've got PIC32MZ with built-in, well, with an attached TFT screen which could display the sample data, but that's using the same pins as the parallel master port, so can't sample through that on it, so that wouldn't work. So yeah, I'm thinking Raspberry Pi probably would be the more sensible option, at least for now, with the option of maybe using a PIC32MZ or an RP2040 or something, possibly. I don't know. I shall have to experiment and see. So I think that's it for tonight. Let me know your thoughts on this. Find me on Discord. I've got my Discord channel, which is it's all linked from my channel here on Twitch or on YouTube, wherever you happen to see me. Yeah. Find me on Discord if you want to discuss this and throw your ideas into the mix. Especially when it comes to how to handle the problem of palettes and 256 colour mode. Because I can't see that being particularly practical. I'm going to have to effectively manually load in palettes for 256 colour mode, which is going to be different for every game, which is not going to be fun. So I really don't know how best to handle those. So yeah, find me on Discord and we'll talk it over, or if you know my email address, then by all means drop me an email. Follow me on Twitch to see progress with this, or subscribe on YouTube if you prefer YouTube and watch this after the fact. I tend to upload all these as sort of view-on-demand things to YouTube. It'll stay on Twitch for the next week as well. So yeah, that's progress. It's partially promising. Partially, why the hell did they do this and what's the point of it? I can see it for the standard sort of 16 colour modes and things like that, it would work fine. And for the full colour modes and 16-bit colour modes, it's fine if you know that you're in that mode. But when it comes to the palette mode, why? What possible use could that actually have over the feature connector? I mean, it's easier to provide it than not provide it, because if you're providing that raw connection, it's just the raw data. But what possible use could it have over the feature connector if you haven't got a palette to compare it to? So I really don't know which way to jump on how to do the palettes, or which system to use. But as I say, it'll probably end up being the Pi. So my next stage really is to set up a Pi, create an image and set it up ready for programming, and experiment with the GPIO interface, which might be fast enough under the operating system. I'm not sure. Because it goes all through the /sys file system normally. And I don't know if I'll be able to get the full sort of 85 or 75 megahertz sampling frequency out of that I would need. But we'll experiment and find out. That'll be a job for another day. For now, I think I'm done for the evening. Time to freshen up a bit, and it's getting very stuffy in here with it. Thunderstorm outside, all the windows closed, doors closed, me rabbiting on, creating so much hot air. Computer's pumping out hot air, it gets a bit stuffy in here, so I think it's time for me to finish. So, yeah, thank you for watching, and catch me next week. Hopefully I won't be late next week.